Here we come! Alright. Greetings and welcome, friends of all ages, people who believe diamonds come from carrots. Today we're talking about polar and rectangular coordinates. That's right, you've been friends with rectangular coordinates, you've been friends with polar coordinates. Wouldn't it be great if they could all just get along, or if there was some sort of mathematical portal that you could pass through to go from one dimension to the other?
No, that wouldn't be great.
Wouldn't it be great if there was some way to convert from polar to rectangular coordinates, just like how we wish there was a way to convert between metric and English standard? There's not. I'm pretending, I assume, maybe. But nonetheless, that's what we're doing today. Let's discover a conversion between the two. Suppose I've got like this, I don't know, like this point right here. All right. We'll draw a little picture here in polar form. So here's my classic r comma theta, non-generically at r and theta there, right? And if I want to convert from polar form to rectangular form, I kind of want to rectangularize this, so to speak. So what I'm going to do is I'd be interested in knowing the over-under on this problem. I believe, right? Right? So if I could find this and this, that would be my x and y, right? For the rectangular location of that point, perhaps. So rectangularly speaking, this would be my x, this would be my y, and the point would also be x comma y. So I want to figure out a relationship that converts from r theta to x, y. And in order to do so, let's think about this. What distance is this purple line in terms of my previously labeled locations? What? Oh, yeah, this would equal x squared plus y squared once it square roots that number, yep. Or what about polarly speaking? What's this length? R. And what is this angle? Theta. Correct. So, and this, of course, being a right angle over here, because that's how the rectangular coordinate system works. Although, theoretically, you could have a pair of oblique axes, I believe is how I could describe them. Wouldn't that be weird if we had a rectangular coordinate system that was more like a parallelogramic coordinate system? It's possible, and actually just as efficient, just not maybe as math friendly. So discovery, here we go. Is there a relationship between x, r, and theta that I could derive? Well, it's a right triangle. And from this angle's perspective, x is the adjacent leg, and r is the hypotenuse. So sine theta would equal x over r. So if I wanted to, I don't know, multiply both sides by r, I would end up getting x equals r times sine. Nope. Nope, guys, you didn't save me on the sine. I messed up. Adjacent to hypotenuse? That is so cosine. Oh, terrible. Yep. So x would equal r times cosine theta. There we are. And that would be a conversion formula to go from, right, rectangular x to r or theta, right? Similarly, y is the opposite leg over here, and r is still the hypotenuse. So that would be sine theta equals y over r, and therefore y would equal r times sine theta. So now it turns out if I know x and y, I could solve a system in order to solve r and theta. If I know r and theta, I could calculate x and y according to these formulas. Good times, good times. So let's take a gander at this right here. So in order to convert from polar coordinates to rectangular coordinates, it says the rectangular coordinates of x comma y, a point by the polar coordinates. Sorry, let's see. The rectangular coordinates x comma y of a point. I'm assuming I'm missing some words here. To convert to rectangular coordinates, whatever. Anyways, the polar coordinates r theta can be found using the following formulas. X equals r cos theta and y equals r sine theta. Now, we're going to want to know these very well, so well in fact that they would behave in some solving equations and manipulations the same way we've been using trigonometric identities, where I could be like, oh, there's an x, I'm going to swap it out for an r cos theta. So we'll want to kind of keep these in our bag of tricks to keep relying on as the need arises. So let's use these then, and let's do some converting. Here's an example. Coming at you. Find the rectangular coordinates of the point 5 comma pi over 3. So r is equal to 5, theta's, my pi is over 3. And if I want to find x, I've got x equals r times cos theta. Also, these formulas really are super similar to some of the ones we dealt with vectors back in the day when we were converting, to horizontal and vertical components. It's actually pretty much identical stuff that we were doing then. But we're just viewing the world differently now. That's fine. So to find x is going to equal 5 times cos of pi over 3. What is cos of pi over 3? That's cos of 60, so I believe that's a half. So x is going to equal 2.5. Right? And y is going to equal 5 times sine of pi over 3. Sine of pi over 3, you might recall, is the same as sine of 60, which is root 3 over 2. Or y is going to equal 2.5 times the square root of 3, or, tell you what, I'll find a decimal approximation of that. That is not what I just plugged in a calculator. 3. There we are. That's about 4.3301, roughly. So that means this point is the same as 2.5 comma 4.3301. And really all that I did in order to do that was a little bit of trig, and then I put it into a nice little formula package for you. So you are most welcome, my friends. Let's do another quick example. Alright, here we are. No, I was thinking actually of the Halo theme song at that point. So let's see, it says find the rectangular coordinates of the point. Same idea. I've got my r, negative 13. I've got my thetas. Don't hate the thetas. Let's see, negative 13, negative 70 degrees. So to find x is going to equal negative 13 times cosine of negative 70 degrees. And y is going to equal negative 13 times the sine of negative 70 degrees. Now, I mean, you can still work with all your crazy reference angle stuff or figure out your quadrants and all that. So this is going to equal x equals cosine of negative 70. Negative 70 is in the fourth quadrant. Cosine should be positive then. And I multiply that by negative 13, which is going to re-negativize it. And I get x equals negative 8.233. And over here, y is equal to sine of negative 70. That's actually going to give me a negative number. In fact, it's equivalent to negative sine of 70. And multiply that by negative 13. It's going to positivize it. and I get 10.0606. Let's see. Oh, let's see if this actually makes sense. Let me grab a snapshot and we'll plot these points. Just verifying -13. I need a coordinate system. All right. Where's my sketch pad hiding? Oh no, you better not pinwheel on me, sketch pad. No. Yeah, it's sketchpad crashed. It's okay. We don't need those geometricians. So it's thinking. It does, yes. Projectors do produce heat. So here we go, friends. Let me see if I can fit this here. Let us take a gander at this problem here.
Oh God, all I can think of is BLTs. I'm so hungry.
So the original point was -13, -70. -70 is like down here, looking that way, right? But -13 would have taken me up this way. So I'm like somewhere up here, right? You agree that's -13, -70 degrees? Yes, okay. So let's think about the triangle based off of that. So rectangular speaking, that should be -8.233, and this should be 10.0606. And I believe that makes sense. Maybe.
No, I don't. Yeah, that doesn't look like it makes sense.
Yeah.
True, because you're like at like 3.5.
Yeah.
-70.
That's like 3.60606.
Oh.
Well, I didn't really graph my angle proper. But anyways, that's the general idea of what's going on. I just wanted to make sure I was in the right quadrant. But yeah, so anyways. And I ran out of room at the bottom of the page. That's fine. So let's take a look at what if I want to convert the other way. Now, this is actually going to relate to Miranda made a comment earlier, I think, regarding some Pythagoras. Yeah, she did. And it turns out we're going to use that Pythagoras technique when converting the other way. So this is kind of just all the same jargon at the beginning, but let me give you my 3 separate equations. Where's my mouse at? Here we are. So you don't necessarily need to write down all that intro again, but here are our 3 awesome equations for converting the other way.
I like the other one better.
Yeah.
What is arctan?
Arctan, remember, is the same as, or similar to tan inverse.
Is it the same or is it different?
Capital arctan just has a restricted domain, so that way the inverse is still a function. But it behaves the same way. So arctan is the same as, or arctan of some value is the same as tan inverse of some value. All right.
Sounds like a name. Some guy.
Arctan, man, yeah, that does sound.
Some guy that Thor would know.
I bet Thor knows how to calculate an arctan. Actually, arctan, like it even sounds like electrical with like an electrical arc from like lightning. Yeah, definitely. So notice first of all, r is equal to x squared, all that good stuff. I'll draw a little picture over here. So imagine I've got my little right x over here, y up there. I've got my like little right triangle. And if I want to find the r from this, here's the r. This would make sense, definitely. You guys absolutely agree with this for calculating r. That's just straight up pi thag. Now, if I wanted to find theta, however, all right, if I want to find this theta, I'd ask the question, okay, I currently would know of I would have known x and y. That is the opposite and the hypotenuse. So I could have started with the concept of tan theta is equal to y over x. So therefore theta would equal tan inverse of y over x. And now I actually considered not including this like whole pi thing going on. You'll be okay as long as you know how to do reference angles. You don't have to worry about any of this pi stuff. If you want to just memorize a formula and use it, this formula works great. If x is positive, then you just do this. If x is negative, then you just have to add pi to whatever your answer is, or 180 degrees if you're working with degrees. Okay, so don't get scared off by this. This is all it's essentially doing, but you just have to play it smart using reference angles if you don't want to memorize that thing going on there. But it just kind of takes care of it for you, which, seriously, why would we want it to do that? So let's do some examples with this. Transitional music. Well, the problem gets up on the screen. Here it is. Find the polar coordinates of the point, blah, blah, blah. So I would like to indicate that x is equal to -8 and y is equal to -12. Now, without the directions, hopefully you'd be able to figure out that this was a rectangular coordinate because there wasn't like any degrees up there or any weird pi's. I suppose -12 radians does exist, so maybe that could have thrown you off there, but yeah. So I'm going to be looking for r. So the formula I'll use is r equals the square root of x squared plus y squared. So I'm just like straight up plugging and chugging. So r equals the square root of -8 all squared plus -12 all squared. So r is equal to the square root of 64 plus 144. Let's see, what's that? Is that 208? Yeah, and then square rooting that number. I get r is about, that's the ugliest r I've ever seen. 14.4222. So there's my r value, not to be confused with the thermal efficiency of insulation or building materials. Am I right? Oh man, guys, you have no idea. That was gold. That was gold right there. So let's see, theta is going to equal, I'll just call it the tan inverse of y over x. And we'll do a little bit of thinking on this one. Theta is going to equal tan inverse of -12 over -8. So now, if, I got to be careful here. This is likely going to give me the reference angle. So I'll just call this alpha real quick. If I type tan inverse in my calculator and do 12/8, because the minus signs cancel out. Am I on radians? I am. So yeah, you guys want degrees? Let me just do degrees just to not scare you. This is 56.3099 degrees. Now question, which quadrant am I in? Tan inverse of this, it came from a calculator. Yeah, calculator told me.
You're in 3.
I'm in quadrant 3, how do you know?
Because you're at 56, thing.
Right, -8,
But then,
-12. That's quadrant 3, you're right. Right, here's quadrant 1, here's quadrant 2, right, and then here's quadrant 3. That's a sad looking 3. There we go. So, so my angle, referentially speaking, this is the 56. How do I find the entire theta? Add 180 to it. And now, if I didn't want to do all that reference angle work, I could have just like straight up added 180 to begin with, because I would have realized, oh, x is negative. So their formula is kind of nice as a shortcut, so to speak, where you don't have to then worry about that stuff. So theta is going to equal 180 more than that. I'll just write 180 plus alpha.
Where does alpha come from?
Your calculator will typically give you a reference angle for stuff, so you just have to be careful. Or technically, tan inverse in your calculator behaves a little bit like arctan, where it's only going to give you a positive or negative value, but never anything bigger than 90 or less than 90 degrees is why we have to kind of like...
How did you know to put that at quadrant 3? You found 56.30.
Based off of these values. So I said -8, -12. That point would have been in quadrant 3. And that's why I knew that I had to take this reference angle and add 180 to it. Right. So so there's the point. That's not that crazy. So I mean, converting points back and forth, we could do that all day with our eyes closed. Maybe. Right? But what if
You wouldn't be able to see the problem.
blind people can do math too, I assume.
Or can they?
Maybe.
Discriminating against blind people? Maybe an idiot.
Whoa.
Actually, I don't know what math looks like in Braille.
She was blind and deaf.
And we for a while.
Huh?
And she was weak for a while, and then she
Yeah.
So,
Yes.
guys, this problem, man, this problem be crazy.
Is this kind of like taking up a lot of room? Is that...
No, not this one. But I do have another example. That'll take up the rest of your room. Yeah, we're good. We're good. So I want to convert from this polar equation into rectangular form. Now, this is crazy. Now think about what tricks I've got. These are the tricks I've got up my sleeve. I've got, regarding cos theta, I know that x equals r times cos theta. All right? So if I could get some sort of r cos theta in here somewhere, that would be nice. Regarding r's, to get rid of r's, I know that x squared plus y squared, if I square root it, that's equal to r, or that's just straight up equal to r squared. All right, so I'm trying to like preemptively think of some of the formulas we just learned today that might help me convert. Now this step, I agree, is not obvious. Sometimes mathematicians play with numbers or with functions until it works out. But I'm expecting you to, once you see this step/trick move or whatever, that you'd at least try to, preemptively think about how to do these in other situations. So let's see. So I've got r equals 6 cos theta. What I'm going to do, I know I can work with r squared. I know I can work with r cos theta. How could I get either of those situations from this?
X equals 6 cos theta squared.
Where?
That's what I said.
That's no guarantee though, because that's assuming that r would equal 6 all the time.
Plug in.
Watch this.
Yeah.
Yeah, get right out of town. And now I could substitute in here and here. And I think that's going to get rid of all of my r's and thetas. So multiplying both sides by r gave me an r cos theta, which I liked, and then also gave me an r squared, which I knew how to deal with. It. So x squared plus y squared equals 6 times, what's r cos theta the same as? X. And this is now in rectangular form. Actually, if you wanted, you could even convert this and realize that it's a circle that's offset. All sorts of crazy things.
Where does that x come from?
Because r cos theta is x.
Yeah, right here. R cos theta equals x. So let me graph the original problem. 6 cos theta. And you can see that the original graph, polarly speaking, was just an offset circle with a center at 3, 0 degrees, if you wanted to think about it that way. So in terms of rectangular form, this would have been the same as, by the way, this would have converted. I'm not going to take the time on it. X squared plus y minus 3 all squared equals r squared. What was the radius on that circle? Looks like, yeah, 3. So 3 squared is 9. It turns out if you could convert this to this using some conic tricks, but this is fine for now. This is all they were looking for. So we're good with that. So I just wanted to point out that it worked. It worked. So good stuff, good stuff. Let's take a look at one last problem. What if I wanted to convert the t'other way around? And this, actually, I don't even know if I'll be able to fit this whole problem. I'll do my best. Besties, here we go. All right, so actually, oddly enough, this is another, that's almost the same equation as before. It's just offset in another direction. Actually, wait a minute. Yeah, I messed up on that, guys. Yeah, well, this one I messed up on. The -3 should have been tucked on with the x there. Sorry about that. Sorry. Yeah, it's the same problem. Well, but let's talk about how we could convert it back. There we go. All right. Crazy sauce. So,
How did you get that from the?
just pretend it's an entirely different problem. Unrelated. My problem was that the graph, I put the -3 on the y, which would have been a circle down here, centered at -3 there. Sorry, it would have been +3. Even worse, I'm making more mistakes. Technically, it was a circle on the x-axis shifted 3, so that's why the -3 would have had to be over there. From this to this, you don't even have to.
Okay.
This is just a bunch of conic work can do that. It's related to completing the square and all sorts of stuff. Go check out some of my other videos, my near 500 videos. Yeah. So anyways, well, actually, he probably has like a couple thousand more than me. All right. Now, if I want to replace this x and y, what tactics do I have to do that? Well, what formulas relate x and y to r's and thetas? I know that x is equal to r cos theta. And I know that y is equal to r sine theta.
That's earlier.
Yeah, that's the beginning of the lesson. So my first move is I'm going to substitute for those guys. So parentheses r cos theta -3 all squared plus r sine theta all squared equals 9. So technically I've got it written in terms of r's and thetas. Let's do a little bit work, see if we can get it all the way back. Now on this guy right here, you might recognize, oh, this is a pattern. I've got to do some a squared minus 2ab plus b squared to that. You of course have that pattern memorized. So that's going to look like this. A squared r cos theta squared minus 2 times r cos theta times b, which is 3, plus b squared, which is 3 squared. And then r sine theta all squared, that's the same as plus r squared sine squared theta equals 9. Craziness. So, let's simplify some of this. This is r squared cos squared theta minus 6r cos theta plus 9 plus r squared sine squared theta equals 9. I could technically eliminate the 9's from both sides by subtracting 9. I'm going to group. Now watch this. Watch how cool this is. I see this r squared sine squared, and I see this r squared cos squared. I think I can factor out an r squared from those terms, and I'm going to be left with a cos squared plus sine squared. Or maybe it's more familiar to you if I write it as sine squared plus cos squared. Or maybe that's more familiar to you if I write it as 1. What? Oh man, yeah, that's one of those Pythag identities from forever ago. So I'm gonna work towards that. So let's factor the r squared out of those two things. So I'd have r squared times cos squared theta plus sine squared theta minus 6r cos theta hanging outside still equals 0. And this whole inside, that's just equal to 1. I'll just say Pythag, ident. All right, so yeah, this stuff's all coming back to us now. So I've got r squared minus 6r cos theta equals 0. And I could add the 6r cos theta to both sides. And I'm almost there. If I divide both sides by r, I can get it in the format that I could plug in to an equation. R is equal to 6 cos theta. And that's going to be the equation of a circle. Or a one-petaled rose, if you want to think about it that way. And in fact, it would look a little bit like this. Bam, right there. So yeah, so converting back was definitely a little bit trickier. I had to, but the main idea is using some of the new transitional form stuff that I can use, right? Some of these equations that will switch x's to r's and thetas and r's and thetas to x's. And then, yeah, the big trick was right here. Dividing both sides by r, I'm still like real cautious about that. I understand if you'd want to leave it like this. Actually, did we have was that one of our forms? The lemniscate? No, that's not quite right. No, that doesn't quite work there. But anyways, so there we go. So thanks for watching, internet friends. You now are hopefully a little bit better at converting between polar and rectangles.